we know how to allocate now into an investment universe that has two risky assets and a risk-free asset. Let's expand our investment universe, and we're going to do this by adding 3 and then 4 and then some large number of risky assets. So not just asset 1 and asset 2, but now asset 3 and then asset 4 and then more. Now, each asset is going to have its own expected return and standard deviation. So we'll have an expected return of 3 and a standard deviation of 3, an expected return of 4 and a standard deviation of 4. But what about the number of correlation coefficients? When we had 2 assets, we had 2 standard deviations, so 2 variances, and 1 cross term, 1 correlation coefficient, rho 1, 2. But technically we actually had 2 cross terms. We had rho 1, 2 and rho 2, 1, but these are equal. The correlation between height and weight is equal to the correlation between weight and height. And so we just multiplied the formula containing these two by 2. And so here I can see my portfolio risk equation, and I just had 2 times the correlation coefficient. Now we could have instead written this: 1 times the correlation of 1, 2, and 1 times the correlation of 2, 1. But they are the same, and so by custom we use this first equation. So let's look at the number of cross terms, the number of correlations, as a function of the number of risky assets. And we'll look at 3 assets, then we'll look at 4 assets, and then we'll generalize for more, and then we'll come back and we'll formally write down our portfolio risk and return equations, given that we have a better understanding of what the number of inputs needs to be. So let's start with a 2 by 2 matrix. And the way I'm going to do this is I'm going to have a 2 by 2 matrix. And I'm going to have asset 1 and asset 2, asset 1 and asset 2. And in this box, this is going to be the relationship with asset 1 with itself. I'm going to end up with sigma 1, 1. Here I'm going to end up with sigma 1, 2. Here I'm going to end up with sigma 2, 1. And here I'll have sigma 2, 2. And all I'm doing is just trying to come up with a way to represent what the cross terms look like. Now I define sigma 1, 1 as the variance and sigma 2, 2 as the variance. And so the terms on the diagonal are variance terms, and the square root of the variance is standard deviations. But let's look at the cross terms, or the off diagonal terms. Here I have sigma 1, 2, and this is going to be sigma 2, 1, but remember that these are equal. And so for a 2 asset case, I have sigma 1 squared, sigma 2 squared. These are the number of variance terms and also standard deviation terms. And for my cross terms, I have sigma 1, 2, and I have 2 of those. Now, a lot of the computations we've been doing, we've been using correlation coefficients. Remember that the correlation is defined as sigma 1, 2 divided by sigma 1, sigma 2. And so even though we're going to be looking at covariance terms here, the number of correlation terms is the same. And so if I have 2 covariance terms, I'm going to have 2 correlation terms as well. So let's add to this. I'm just going to remove a number of these markings here, and let's look at what a third asset looks like. And so I'm just going to expand my matrix to make it a 3 by 3, and I just see what this looks like. 3 by 3, I know I'm going to have sigma 3, 3 here, which is another variance term, another standard deviation term, but here I'm going to have sigma 1, 3, here I'm going to have sigma 2, 3, here I'm going to have sigma 3, 1, and sigma 3, 2. And again, I now have, for 3 assets, I'm going to have 3 times the variance, or, oops, I keep pushing that button, standard deviations, sigmas. But what about unique cross terms, unique covariance or correlation terms? Well, I know that 3, 1 is equal to 1, 3. And I know that 3, 2 is equal to 2, 3. And so now I can see that this term is going to be equal to that term. And this term is going to be equal to that term. This is going to be equal to that. I'm going to have 3 unique, let's go back to black, 3 unique cross terms. And so I'm going to have 3 correlations, or 3 covariances, and let's call that ij. What if I add a 4th asset? So let me get rid of a bunch of these marks, and we'll add a 4th asset. And so now I want to add the 4th asset. Well, again, on my diagonal, sigma 4, 4 is going to be one more variance term. So I have 1, 2, 3, 4 variance terms. But what about my cross terms? Well, now I have a sigma 1, 4. I have a sigma 2, 4. I have a sigma 3, 4. I have a sigma 4, 1, a sigma 4, 2, and a sigma 4, 3. And again, I can see that 4, 1 is going to equal 1, 4, 4, 2 is going to equal 2, 4, 4, 3 is going to equal 3, 4. And so now I can see the number, 3, 1 is going to equal 1, 3. I can see the number of unique terms is going to be 1, 2, 3, 4, 5, 6 unique covariance or correlation terms. The others, the 1, 2, the 3, 1, the 4, 1, these are all going to be repeats of ones that I have already accounted for up here. This is 3, 2. So let's see if we can come up with a general formula for the number of cross terms. I know that my total size of my box is going to be 4 squared, which is equal to 16. But I know that I'm also going to be eliminating the diagonal terms, because the diagonal terms are going to be variances. So it's 4 squared minus 4, which is going to be 16 minus 4 is 12. So there's 12 remaining boxes, but I know that half of these are going to be repeats. And so I'm going to end up with 16 minus 4 over 2 is 6 unique terms, and that's the number of green circles that we counted earlier. In general, the number of cross terms is going to equal, n squared, which is the size of my matrix, minus n, which is the number of diagonal terms, which are variant terms, and therefore not cross terms, divided by 2, because they're going to be doubles. And so again, the number of cross terms, which are covariants or correlations, is going to equal n squared minus n over 2.